We'll look some more at graphs of relations and functions, and the question we're going to look at is how can you tell from a graph where something is a function or not? And what we do, because if we think about what's the definition of a function, the definition of a function was that each x value had only one y value. As soon as an x value has more than one y value, it's not a function. So a way to tell whether a graph is a function or not is something that is a vertical line test. Because if you draw a vertical line, there we go, nice vertical line, and I take that vertical line and move it along, that's going through every x value, and as it hits the graph at a y value. If it only hits the graph at one point, then every x value has one y value. But if the vertical line hits the graph twice, that's saying here at this x value, there's two y values. There's one that's positive and one that's negative. So this circle would be a relation, but it wouldn't be a function. This next one, as I go through, do I ever hit the graph more than once? Ooh, it's close. But it doesn't look like I hit the graph more than once. So that would be a function. So we could say this first one is a function. The second one is not a function. And the third one is a function. So we slide that vertical line across the graph. If that vertical line touches it more than once, then the relation is not a function. And it has a nice name for helping you remember what it's supposed to be, the vertical line test. If a graph is a scatter plot, right, you can still use the vertical line test. Draw your vertical line. Check each point. Only hit one, only hit one, only hit one, only hit one, 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 one. This one will be a function. But over here, is there any place I could put my vertical line that would hit more than one point? Yes, right there. I would hit more than one point. So I could say this one is a function. This one is not a function. They are both still relations. Anytime you can do anything that connects two things together, it makes a relation. Yes? Yeah. Example 3. The relationship between height and shoe size. Identify the dependent and the independent variables. So remember, our dependent variable is always on our y-axis, and our independent variable is always on our x-axis. So in this case, the dependent is height, and the independent variable is shoe size. Does your height depend on your shoe size? Yeah. Knowing someone's shoe size can tell you a little bit about their height. You could do this the opposite way too, right? It's probably, if you saw me, you would say, I don't think he would fit into a kid's size 2 because of how tall he is. That would make sense. So you could, this one, you could probably graph it either way and say they both depend on each other depending on which way you're thinking about it. Okay? Give the domain of the relation and say if it's a function or not. So, wow, that's a bad squiggly bracket. Oh, yeah. Domain. Those are your x values. Those are your independent values. If we go through here, it looks like we have a 7, a 7.5, an 8.5, a 9, and a 10.5. Is this a function? No. We can draw a vertical line. A vertical line that goes through more than one point. So this is not a function. Oh, we didn't do the range. The range, we've got, we're going to have to do some estimating here. Looks like the smallest value, are you okay if I say that's 167, 168, 170, 175, 178, and 188? So I'm estimating those y values. We have to kind of guess just based on where they are on the graph. Why are the points not joined? Why don't I make this the graph? Why doesn't that make sense to do? Or what happens, would it make sense if I did this just as an estimate? What are some of the characteristics of the situation we're thinking about that it doesn't make sense to draw a line? Well, it's not a function, but sometimes you can take something that's not a function and estimate it with a function. But there's some reasons why we wouldn't want to draw a line in this case. Well, it might not be linear. But what's the problem with, if I did connect the dots, let's say even if I just connected the first two. There's a problem with connecting those first two. 3/8. Yeah. This would say there's a shoe size in between 7 and 7.5. Okay? Go into a shoe store. When the person says, "Can I help you?" say, "I'm looking for a 7 3/8 shoe. Do you have any?" And when they say no, ask if you know where you could find one. What would the reaction be? Okay? They're like, "Yeah, get out of here," because you're supposed to know that shoe sizes don't come in 7 3/8. They don't exist. So how do we work with that? Question or just?
Probably estimation.
Okay.
Yeah. Is that like, we know for a line because it's like an average or something?
Well, the line, if we connected them, it would mean that there would exist shoe sizes in between 7 and 7.5. And there's only dots here because you can't have shoe sizes in between. Your foot, though, if you measure your foot, it's not like your foot grows in half sizes. It's not like all of a sudden your toes just start shaking and all of a sudden they go blip and they jump forward a centimeter. That would be weird if people grew that way, right? It grows continuously. So if you were measuring the actual size of a person's foot, it would make sense to draw the line. But when we're talking about shoe sizes do go up in blips. You don't have that 7 3/8 size in between. So why are the points not joined? You can't have So you'd have to somehow describe this. So you can't have shoes between certain sizes. For example, no 7 3/8 size. So we could describe it that way. Or you could describe it, why are the points not joined? Shoe sizes only come in whole numbers or halves. So you could describe it that way too, as a way to say, why is it that we don't join the points on this graph?